All right, so ready to dive into another fascinating paper.
Absolutely. Always excited to see what the research world is cooking up.
Today, we're looking at Object-Centric World Model for Language-Guided Manipulation. Quite a mouthful, but trust me, the concept is even cooler than the title.
Yeah, I got a chance to skim it, and it definitely seems like it's pushing some boundaries. So before we get lost in the technical weeds, maybe a quick elevator pitch for our listeners. What's this paper all about, and why should they care?
Okay, imagine a robot. Right? Not just any robot, but one that can understand its surroundings, predict what's going to happen next, and then use that understanding to actually manipulate objects.
Sort of like a robot that can think ahead, plan its moves, and get things done based on what you tell it to do.
Exactly. And that's where this idea of a world model comes in. It's basically a model that can simulate how the world works, how objects behave, and how actions lead to consequences.
So if you tell this robot, hey, put that blue block on top of the red one, it can actually visualize those actions happening in its mind before it even moves a muscle.
That's the idea. And the exciting thing is, this paper is proposing a new way to build these world models, a way that's more efficient, more flexible, and arguably more in line with how we humans perceive the world.
Okay, now I'm really intrigued. Efficient and human-like? Those are some big claims.
It is, and they're doing it by focusing on objects. Instead of trying to predict the entire scene as a whole, they're breaking it down into individual objects and predicting how those objects will move and interact.
Object-centric, interesting approach.
Yeah.
So instead of predicting pixels changing in a video, it's more like, here's a blue block, here's a red sphere, and based on the instructions, this is how their positions and relationships might change.
You got it. And this object-centric view has some pretty significant advantages. First, it's a much more compact way to represent the world. You don't need to keep track of every single pixel, just the essential information about each object.
That makes sense. Less data to process, faster predictions, potentially less computational overhead.
Exactly. And this leads to the second big advantage, flexibility. By using language to guide the predictions, you can instruct the robot to do all sorts of tasks, and the model can adapt and predict the outcome accordingly.
So it's not just pre-programmed to handle specific scenarios. It can actually understand instructions and then figure out how those instructions would play out in the real world.
Precisely. And the authors of this paper are claiming that their object-centric world model not only excels in efficiency and flexibility, but also actually outperforms some of the leading methods out there, particularly those that try to predict future video frames directly.
Now that's a Bill statement. We're talking about going head-to-head with some of the most computationally intensive, data-hungry models out there and coming out on top.
That's what they're claiming, and they've got some pretty compelling experimental results to back it up. But before we get into all that, let's back up a bit and give some context.
Yeah, a little history lesson is always good. How did we even get to this point where we're talking about robots that can understand language and predict the future?
Well, the pursuit of creating AI that can understand and interact with the world the way we do has been a long-standing dream. Right?
Oh, yeah, for sure. I mean, since the dawn of AI, really.
Yeah.
But for a long time, the focus was on symbolic AI, right? Trying to represent the world through explicit rules and logic. Like, if object A is on top of object B and object C is moved toward object A.
Yeah, kind of like programming a computer to understand the world as a giant set of if-then statements.
Exactly. And while that worked okay for very simple controlled environments, it just didn't scale to the complexity of the real world. Too many variables, too many exceptions, too messy.
Right. And then came this wave of data-driven approaches, fueled by the rise of deep learning and neural networks. Suddenly, instead of trying to handcraft rules for everything, we could feed massive amounts of data to these models and let them learn the patterns and relationships themselves.
That was a huge turning point, wasn't it? Instead of telling the machine how to think, we started showing it examples and letting it figure things out on its own.
Exactly. And that led to some remarkable breakthroughs in areas like image recognition, speech processing, and machine translation. But when it came to building world models, especially for robotics, the challenge was still immense.
Yeah, because now you're not just dealing with static images or text. You've got this dynamic, constantly changing environment that the AI needs to make sense of, all while trying to control a physical body in that environment.
And that's where things get really tricky. I mean, imagine trying to predict how a scene will unfold, even just a few seconds into the future. There are so many factors at play, from the physics of objects to the intentions of other agents.
And not to mention the sheer amount of data involved. High-resolution video streams, complex sensor readings, language instructions. It's a lot to process in real time.
Which brings us back to this paper and their proposal for a more efficient object-centric approach. They're essentially building on those earlier breakthroughs in representation learning and object recognition, but applying them to the problem of building world models for robotics.
Okay, so let's dive into the paper itself. Where do they start?
They start by laying the groundwork, emphasizing the importance of world models in AI research as a whole. And they're not just talking about robotics here. They cite examples from all sorts of fields like autonomous driving, game playing, and even scientific discovery.
World models as a sort of universal tool for AI, helping it to understand and reason about the world around it.
Exactly. And then they quickly zoom in on the recent trend of using video generation techniques, particularly those based on diffusion models, to build these world models. And this makes sense, right? If you can generate a plausible future video of what might happen next, you've essentially captured a lot of the predictive power you'd want in a world model.
Yeah, and those diffusion models have been making waves lately, producing some incredibly realistic images and videos. So using them for world models seems like a natural next step.
It does. But, as the authors point out, there's a catch. These diffusion-based models, while powerful, are incredibly data-hungry and computationally expensive.
Ah, the classic AI dilemma. Great results, but at a hefty cost.
Right. And that cost, in terms of both data and computation, becomes a major bottleneck when you're talking about real-time applications like robotics. You can't have a robot waiting hours for its world model to generate predictions. It needs to react and adapt in real time.
So that's the problem they're trying to address. How to build a world model that's both accurate and efficient enough for practical use.
Exactly. And their solution, as we've hinted at, is to focus on objects. Instead of trying to predict everything that might happen in the entire scene, they zoom in on the individual objects and how they're likely to move and interact.
And this is where the slot attention mechanism comes in, right?
Yes. They utilize this technique to essentially carve up the scene into these distinct slots, each representing a separate object. It's like the AI is saying, okay, here's a slot for the blue block, here's one for the red sphere, and here's one for the robot arm.
And then instead of predicting what every pixel in the scene will do next, it's predicting how these object slots will evolve over time.
Precisely. And they're doing this in a way that's guarded by language instructions. So you can tell the robot, put the blue block on top of the red sphere, and the model can use that instruction to predict how the slots representing those objects will change.
So they're combining this object-centric representation with the power of language understanding to create a more targeted, efficient world model.
Exactly. And they're claiming that this approach has several key advantages. First, as we've discussed, it's more efficient, less data, faster processing.
That's always good.
Second, it's more flexible. Language provides a natural way to express a wide range of tasks and goals.
And humans are pretty good at giving instructions, especially vague ones.
Right. And third, it's arguably more intuitive. For tasks that involve object manipulation, understanding individual objects and their properties is crucial.
Makes sense. If you're going to pick something up or move it, you need to know what it is and where it is.
Exactly. So they've set the stage, they've explained the motivation, and they've laid out their core idea. Now let's delve into how they actually built this model.
Yeah, let's get into the nitty-gritty details.
So their model consists of two main components, a slot encoder and a world model.
The classic encoder-decoder setup. What does the encoder do?
The encoder is responsible for taking the raw visual input, in this case a video stream, and extracting those object-centric slots. They actually use a pre-trained model called SAVI for this purpose.
AZ, okay. And that's specifically designed for this kind of object-centric representation.
Yes. SAVI is all about identifying and tracking objects over time, which is exactly what we need for this world model.
So it's like SAVI does the initial heavy lifting of segmenting the scene and figuring out, okay, these pixels belong to the blue block, these belong to the red sphere, and so on.
Exactly. And then it outputs a set of these object slots, each containing a compressed representation of the object's properties, like its position, shape, and appearance.
Got it. So the encoder gives us these object slots. What happens next?
That's where the world model comes in. It takes those object slots, along with a language instruction, and predicts how those slots will change over time.
So it's like, here's the current state of the world, here's what I want you to do, now show me what happens next.
Exactly. And they're using a modified version of a model called Slotformer for this purpose. They call it L-Slotformer, where the L stands for language.
So the L indicates that it's specifically designed to handle language instructions.
Precisely. They've integrated the language instruction directly into the architecture of the model, so it can use that information to guide its predictions.
Okay, so we have the savvy encoder giving us the object slots, and the L-Slotformer predicting how those slots will evolve. What about the actual actions? How does the robot decide what to do?
That's where the action decoder comes in. It takes the current object slots, the predictive future slots, and potentially the language instruction again, and outputs a predicted action.
So it's like, here's where the objects are now, here's where I predict they'll be, and based on that, this is the action I should take.
Exactly. And they experiment with different action decoding mechanisms, different neural network architectures to see what works best.
So they're not just relying on one specific method. They're exploring different options to figure out the optimal way to translate those predictions into actions.
Exactly. And then, of course, they need to evaluate this whole system. How do they actually test whether it works?
Right. The proof is in the pudding, as they say.
So they use a simulated robotic environment called the language table dataset. It's basically a virtual tabletop with a robotic arm and a set of blocks.
Kind of like a virtual playground for testing out robotic manipulation tasks.
Exactly. And they define a set of tasks like put the blue block on top of the red sphere, and then they evaluate how well their model can solve those tasks.
And how do they measure success?
They look at things like success rate, basically how often the robot completes the task correctly. And they also look at efficiency, how long it takes, and how much computation is needed.
Makes sense. Accuracy and efficiency, the two key metrics.
Exactly. And they compare their model against several baseline methods, including some state-of-the-art video generation models.
Okay, so they're really putting it to the test, seeing how it stacks up against the big players. What were the results?
Well, the results are actually quite impressive. They found that their object-centric world model consistently outperformed the baselines, both in terms of success rate and efficiency.
So not only was it more accurate in completing the tasks, but it did so using less computation and less time.
Exactly. And this suggests that their approach is indeed more efficient and arguably more effective for this type of language-guided manipulation task.
Interesting. So it's not just about the novelty of the approach, it's actually delivering tangible benefits in terms of performance.
Exactly. And they don't stop there. They also conduct a series of ablation studies to really understand what's driving those results.
Ablation studies, those are always interesting. It's like taking the model apart piece by piece to figure out which components are really essential.
Exactly. And what they find is that the world model itself, this ability to predict how object slots will evolve, is crucial for success.
Makes sense. If you can't accurately predict what's going to happen next, it's going to be pretty hard to plan effective actions.
Right. And they also find that the way they integrate language into the model is important. Just having the language instruction isn't enough. It needs to be used in a way that actually guides the predictions of the world model.
So it's not just about understanding the words. It's about using that understanding to shape the model's internal representation of the world.
Exactly. And then they do some interesting analysis on the quality of the predicted videos. And while their model doesn't necessarily produce the most visually realistic videos compared to those diffusion-based models, it does capture the essential dynamics of the objects and their interactions, which is what really matters for the task at hand.
So it's prioritizing accuracy and efficiency over visual fidelity, which makes sense for a task that's focused on manipulation rather than pure visual generation.
Exactly. So, to sum it all up, this paper presents a compelling argument for a new way of building world models for robotics, an approach that's more efficient, more flexible, and arguably more intuitive, based on this idea of focusing on objects and how they interact.
And it's not just a theoretical idea. They've shown that it actually works in practice, outperforming some of the leading methods in the field.
It's a pretty significant contribution, and it definitely points towards an exciting direction for future research.
Now, speaking of future research, it's time for our favorite segment, Novel Notions. What are your thoughts? What intriguing extensions or related ideas come to mind when you think about this work?
Well, one thought that struck me, and it's actually something the authors themselves mention as a potential limitation, is the deterministic nature of their current model.
Meaning that it predicts one single, definite future based on the current state and the instruction.
Exactly. And while that's a good starting point, it doesn't quite capture the inherent uncertainty of the real world. I mean, things don't always go exactly as planned, right?
Right, especially when you're dealing with robots and physical objects. There's always a chance of slippage, collision, or just unexpected variations in movement.
Exactly. So my novel notion is to explore the integration of probabilistic reasoning into this object-centric world model framework. Instead of predicting a single future state for each object slot, the model could predict a probability distribution over possible future states.
So instead of saying the blue block will be here, it would say there's a 60% chance the blue block will be here, a 20% chance it'll be slightly to the left, and a 10% chance it'll.
Exactly. It would provide a more nuanced, probabilistic view of how the world might evolve. And this could be really valuable for planning more robust and adaptive actions.
Right. If the robot knows that there's a chance of something going wrong, it can factor that into its decision-making and potentially plan for alternative outcomes.
Exactly. It could lead to robots that are less prone to errors and more capable of handling unexpected situations.
I like it. A probabilistic, object-centric world model.
Right.
What's your second novel notion?
Well, the other thing that really stood out to me is the potential of combining this object-centric approach with the power of large language models.
LLMs, the darlings of the AI world these days. They're popping up everywhere.
They are, and for good reason. They've demonstrated some incredible capabilities in understanding and generating human-like text. So imagine if we could integrate a really powerful LLM directly into this world model.
Interesting. How would that work?
Well, instead of just feeding the LLM a simple instruction, we could give it access to the entire object-centric representation of the scene. It could see the object slots, their properties, and their relationships.
So it would have a much richer understanding of the context, not just the words themselves.
Exactly. And this could allow for much more sophisticated language understanding and reasoning. For example, imagine telling the robot, make sure everything is organized.
That's pretty vague.
It is. But a powerful LLM, coupled with this object-centric view, could potentially figure out what organized means in that specific context. It could look at the arrangement of the objects, consider their types and purposes, and then come up with a plan to achieve that goal.
That'd be pretty impressive. We're talking about robots that can understand and act upon high-level instructions, not just follow pre-programmed routines.
Exactly. It would be a huge step towards more intuitive and flexible human-robot interaction.
I like it. Bringing together the structured world of objects with the expressive power of language. Two powerful ideas coming together.
Exactly. And of course, there are many other potential avenues for future research. This is just scratching the surface.
Nice. This is just the beginning of the exploration.
So to wrap things up, we've taken a deep dive into this fascinating paper that proposes a new way of building world models for robots. A way that's based on objects, guided by language, and demonstrably more efficient and effective than some of the leading methods out there.
It's a compelling example of how we can leverage insights from different areas of AI research. Object recognition, language understanding, sequence modeling, to create systems that are more capable of understanding and interacting with the complex world around us.
And we've also explored some potential directions for future research, pushing the boundaries of what these object-centric world models can achieve.
Always fun to speculate about where things might go next.
So we encourage all our listeners to check out the paper themselves for a more in-depth look. The link, as always, is in the description below.
And until next time, keep those AI wheels turning.
See you next time.